So today we're going to learn more about energy and chemical bonds, and specifically not just how chemical bonds are formed, like we've been doing in class, but what happens as we start to rearrange chemical bonds, break bonds, and then reform bonds, which is known as chemical reactions. Well, this is all about energy, and we've seen this particular process before, that energy is absorbed and released in chemical reactions, because we've seen chemical reactions before like that. And so when we're talking about certain things that are giving off heat and light, we know that there must be energy that's being released. And this is kind of the secret to the lab that we're going to take a look at tomorrow, is how are we going to release that energy that's stored up inside these particular molecules or compounds and kind of release that bond energy so we can use it. Better blow that up before I make a mess. Anyway, so taking a look at what we got going on today. Chemical bonding is all about energy. Atoms coming together, giving, taking, sharing, trading electrons is all about achieving something known as chemical stability or electrostability. And in all of these cases, the reason why atoms bond together is because bonding makes them more stable. We may temporarily bond them in a less stable way, but eventually those atoms will bond and rebond in ways that makes them as energy efficient as possible, as low energy actually as possible. And chemical reactions will gain or absorb heat kind of related to this. And we've seen endothermic and exothermic reactions before. This is kind of relative to the amount of heat that's sort of going in and out and being stored in these chemical reactions or in these chemical bonds. So this whole process here, by the way, is called thermodynamics. Thermodynamics is the measure or the study, I guess, of how heat changes or energies change in systems, especially in this case chemical systems, but we can talk about thermodynamics of mechanical systems and other kinds as well. So one of the ways that you have understood the law of thermodynamics or the rules of thermodynamics before is called the first rule or the law of conservation of energy. You know that energy cannot be created or destroyed, that it can simply change its form, so that when we are doing things like bonding atoms together or breaking atoms apart, and that energy is coming into or going out of the system, if it's going into the system, it's being stored there. If it's coming out of the system, it's being released there. We're not creating something new, we're simply changing its form. It was in a chemical bond and now it's being released as heat, or it was in heat and now it's being stored in a chemical bond, something along those lines. So with this, a couple main ideas to keep in mind is that bond formation, creating new bonds between atoms, is inherently an exothermic process. Now this isn't necessarily obvious, but this means that atoms, when they come together, like to be together. And as they come together and form new bonds, energy is released from that particular process. They go, ah. Sort of in that way. And so what that looks like to us is the release of heat typically. So like I said, when bonds are being formed, this is a new thermodynamically stable state, that bond, and so the energy doesn't need to be within the atoms. That energy can be released out into the environment, and we can feel that energy that's being released, and it feels like heat. Sometimes it looks like light. There's other things that come along with that, but the new products are actually lower energy than the original reactants. The original reactants had a certain amount of energy that was in them, and when we bond them together now, they kind of drop down to a newer, lower energy state. So you can kind of see this in this bottom graph that's down here, where you'd say, okay, how much energy was in the reactants to begin with? And this is stored up either within the bonds that are already present or within other more complicated things, the structure of the atom itself, but how much energy is in the reactants. And then when we form new products, we see that that energy is kind of at a lower level. That means energy is being released from that system. This energy that's being released, this drop in energy right here, that's what we feel then as being heat. It's being released from inside the chemicals to the outside world. We're the outside world, so we feel it as something that's either warm to our hands or a warm beaker, or it may look like a flame or something along those lines. So again, this is that idea of bond formation is exothermic. They want to form bonds, and when they do, the new products are lower energy state, and that excess energy is given to us in the form of heat. On the opposite side, breaking bonds, getting atoms to come apart, is actually endothermic. We have to put energy into a system. In a sense, we have to crack those atoms apart. They want to be together, and we have to invest energy into that system to get them to come apart. A lot of times we can invest that energy in the form of heat. Heat is a type of energy. We don't literally go in there and snap atoms apart, although catalysts and things like that can basically do that. But we're putting energy into that system. We're providing heat or something else that can get in there and to help move those atoms away away from one another, break those bonds. Those graphs look a little bit different. You can kind of see this one that's on the screen as well, that at the bottom here, we've got the reactance line is kind of on the low side, and we're putting a bunch of energy into that system. So we're setting it on fire, so to speak, perhaps, or putting heat into it, putting our dough in the oven, even if you want to think about that. Energy is being put in there, and new products are being formed. But in this case, these products that are being formed have a different arrangement of energy to them. There's more energy formed inside there. It takes energy to break those bonds. So anyway, endothermic reactions don't necessarily feel cold. Sometimes it necessarily means it's something that you have to make hot. You have to put energy or put pressure into that system in order to get that pressure on there, to get those new molecular fragments to form, so to speak. All right, so when we're talking about the reaction we're going to do, my favorite, which is combustion reactions, we're going to take a look at how we can release the energy that was in some products. We would call those products carbohydrates or something along those lines. And we're going to add a little bit of oxygen to it. Oxygen kind of helps. And then we're going to create some new products. Those new products that are being formed are carbon dioxide and water. And now carbon and oxygen want to bond together. That releases a bunch of energy. And hydrogen and oxygen want to bond together, and that also releases a bunch of energy. So we're going to break some bonds that's over here. We have to put some energy into it. And we're going to form some new bonds over here, and that's going to cause the energy to come out of it. So it's kind of a two-step process. So number one, we have to break the bonds that were already present in our item, like our Fruit Loop, and then we have to add some oxygen to it, and then we have to do something to get this thing going. I wonder if this will work. I haven't tried it yet, so this will be really exciting to see if this will actually go. Do Fruit Loops actually undergo combustion reactions? Ew, this is really gross. Oh my God, this smells really bad. So we're putting some energy into the system to start breaking these bonds, and as we start to break these bonds, we're starting to get heat that's being produced by it. Man, that does not look delicious at this point. And as we're doing this, we're releasing some of that energy. It's coming off as heat. It's coming off as light. You can see this new form that's being in there. So these energy is now changing its form. And we're producing two products that are very difficult to see. They're kind of up here. That's carbon dioxide and water vapor. There it is. Not very exciting. But there's our new products. And then we get some uncombusted stuff down here. Overall, this reaction is exothermic. Hopefully the smoke alarm doesn't go off. Anyway, overall, this reaction is exothermic. Energy is being released from the system from bonds that are being formed. So the bonds that are being formed are these carbon dioxide bonds, and these water vapor bonds are the ones that are being formed, and it's releasing a whole bunch of energy. That energy that was stored up within the Fruit Loop has now been released, and this really low energy product is now left, and we've got a lot of carbon dioxide and water that's behind there. So let's take a look at how we can start to kind of quantify these sorts of combustion reactions, because it's kind of challenging to actually try to capture that energy and figure out what that is. The way that we capture this is through a process called calorimetry, as in calories. When we're talking about the calories that's in your food, it's the form of energy that's stored up in your food. Well, we don't burn it literally with a candle on the inside. We burn it metabolically using some biochemistry, but it's the same idea. We want to get the calories that's in our food, how much energy was in those bonds that we can now release to the environment. So this is called calorimetry, is the name of this process. It's kind of tricky to do this in terms of trying to figure out how many calories were in that Cheeto or in that Fruit Loop to begin with. You can't just look at it and figure that out, and sometimes you can't even just draw it and figure it out. So we're going to take advantage of a trick, which is kind of pictured here on the screen. We're going to do something very similar to this, where we're going to burn some food objects, and we're going to release that energy in the form of heat. Then we're going to take advantage of the first law of thermodynamics, which says that you cannot create or destroy energy. You can simply change its form. So we're going to say that, all right, the amount of heat that's being released by my Cheeto or my Fruit Loop is going to be gained by something else. Now I need to be able to capture that energy somewhere, and what I am going to do is we're going to take some water, and in this container, I know you can't see it because it's a soda can, but we're going to put water inside this can. And so we're going to say, let's fill this up with water. This water is going to get hot. Why? Well, because we're releasing energy from this food object underneath it. This energy is heating up then the water that's inside there, and that's pretty easy to measure because all I got to do is stick a thermometer in there, and I'll know how much energy was absorbed by that water. So the increase in temperature of the water is directly related to how much energy was released by the food item. I don't even know what that was to start with. Kind of looks like a gummy bear. Ew, that'd be gross. Anyway, so we're going to take a look at how to measure this out. So in a little bit more detail, here's how this math works that you're going to do in class tomorrow. You're going to have food items down here that you're going to relatively set on fire, depending on what they are. Like this one's a peanut. It could be your Cheeto. It could be my Fruit Loop. Anyway, you're going to put that item underneath here, and then you're going to have a container that's going to contain a certain amount of water. You'll know how much it is because you'll put it in there, and then we're going to measure the change in temperature of the water using a temperature probe. We won't use a thermometer, but we'll use a change in temperature. And we're going to use this equation that you see on the screen. Now, this equation I know looks a little scary. I'm not testing you on this equation. I just want you to be able to use it. So this is the heat equation, and this is Q equals M times delta T times Cp. So what are all these things? Q is heat, and that's measured in joules in the metric system. In the English system, we measure heat in calories, as in the calories of your food. But in, like I said, the metric system, we measure it in joules or sometimes kilojoules, just to make our units more easy. M stands for mass. So it's going to be the mass of the peanut or the mass of the water. Typically, the water is what we're going to use with here. The triangle T is delta T. What's the change in temperature? So what was the temperature of the water at the beginning? And then what was the temperature of the water after that item had burned up all the way? So you've got to measure both of those. And then this last thing here is something called CP. It's called specific heat. Specific heat is a characteristic of certain types of, or all types of matter. And you guys have an instinctive feeling for what this is. Specific heat is how much energy does it take to heat something up or cool it down. So for example, metals heat up and cool down very easily. I can hold a piece of metal in my hands and it's going to heat up to my hand temperature very, very quickly. It's got a very low specific heat. Water, on the other hand, I could hold, it'd be kind of weird, but I could hold a glass or a cup full of water in my hands. It would take a really long time to warm up that water to body heat. Water has a very high specific temperature. It takes a lot of energy to heat it up or cool it down. The specific heat of water will be given to you. It's not something you have to know, but it's a relatively large number. It's actually 4.184. So anyway, the specific heats of metals tends to be oftentimes less than 1, a much smaller value. So the way that we're going to do this, the math, and I'll show you an example on the next screen, is that number one, we're going to calculate the amount of heat that was gained by the water. So we'll have this container of water, it'll be heated up by the fire underneath it, and then we'll be able to measure the change in temperature of the water, and we'll know all of these pieces, this Q equals M delta T Cp. We'll know the heat of the water because we'll know the mass of the water. You'll be able to figure out the change in temperature of water, and the specific heat of water is given to you. It's just a number, so that'll be given to you. So the second thing is we use this assumption that the heat gained by the water must have come from the food. So the heat lost by the food and the heat gained by the food must have been the same thing. So now I know how much heat was in that food, like how much heat must have been in that poor Fruit Loop. Anyway, once I know that, then I'm going to measure something or calculate something called energy density. Basically, what is the number of joules per gram of Fruit Loop? So if I have something that's really heavy that only makes a few joules of water, or something that's really light that makes it joules of water, joules of energy, versus something that's really light that makes it joules of energy, this helps us to control for the size of the object that we burn. Did you burn a teeny tiny little Fruit Loop? Did you burn a sunflower seed? Did you burn a great big walnut, or like an entire Cheeto or something like that? They have different masses. So this is a way for us to calculate the sort of joules per gram of these particular items. So here's what it looks like. Simple calculations. Don't freak out about this, but here's an example problem. Let's say you burned a walnut. The walnut weighed 5.60 grams under that calorimeter, kind of like shown in the diagram. The calorimeter has 93 grams of water, about 100 milliliters of water, not quite. And the temperature increases from 21.4 to 29.7 degrees Celsius as that walnut burns. So while you're sitting there waiting for that walnut to burn, you're just sort of stirring and measuring the change in temperature of the water, and you got those values. So here's how the math works out. So number one, calculate the heat that was gained by the water. So that's step one right here. You're using that Q equals M delta T Cp. It's really important that you're using all the information about water in this case. So this is the mass of the water, the change in temperature of the water, and the specific heat of the water. And so in this particular case, if the temperature heated up that much, then I know that 3,230 joules of energy must have been absorbed by the water to get the temperature to increase that amount. And that's rough sig figs, about 3 sig figs. Okay. Second piece of our logic here is that the energy that was gained by the water must have been lost by breaking and forming all those bonds in this stuff, right? We broke all the bonds that were in the Fruit Loop, and we created all these bonds in the carbon dioxide and water. So that energy change must have come from this process. So that means that the amount of energy that was in our original Fruit Loop must have also been 3,230 joules. Heat gained equals heat lost. And then the last thing is we're going to calculate our energy density of our walnut. And in this case, we would say, all right, 3,230 joules of energy must have been released by that walnut. And that walnut weighed 5.6 grams, so it's 577 joules per gram of walnut. That's how you do the simple calculations for calorimetry, and this is what we're going to do in class. Yeah, bird stuff. So, just to kind of review, chemical bonds are all about energy, and that chemical bonds are a way for atoms to achieve stability by forming bonds, or we can, by forming bonds, or we can break bonds to pull them apart. And these processes are either endothermic or exothermic. The formation of bonds is exothermic. The breaking of bonds is endothermic. So in order for atoms to come together, they're going to release energy, and us to break them apart is we have to put energy into that system. It's endothermic. Chemical reactions overall are going to result from the kind of that net change. How many bonds are being broken and how many bonds are being formed. So as long as that net change is negative, I know it sounds really weird, heat's going to come out of that system and it'll be exothermic. If the overall change there is a matter of breaking bonds, investing energy into that, that's going to be endothermic, and we'll have to put energy into it or it'll feel colder to us. Energy changes are always measured in terms of the amount of heat, which is basically measured by us in terms of temperature. So temperature absorbed or temperature released is related to the amount of heat. And then the last thing is that we took a look at calorimetry. Calorimetry is a lab technique that we use to measure the amount of energy that was stored in food items. And we do this by creating new bonds. Those new bonds are the bonds between carbon dioxide and the bonds between water. And that releases a whole bunch of energy for us that we can then measure. And we trap that energy in some water, and we do a little bit of math magic to figure out energy gained equals energy lost. So this is the basic ideas of thermodynamics, energy in chemical bonds, and how we can kind of move energy into and out of systems or around in systems from one kind of a bond to another kind of bond to either absorb heat or release heat. Hope we have fun burning stuff in class tomorrow, right? Fire!